Hello everyone, my name is Pritam Paul and welcome to another video. And in this video, we are going to talk about a new topic which is a AVL tree. Now, what is AVL tree? We have to talk about what is AVL tree, need of AVL trees, okay, and how the concept has came, okay, how the concept has came, and like what are the basic structures, like basics of AVL trees. We would be talking about that. Okay, so in this video we will be talking about all these things. Now, before starting with AVL tree, we have to go to the binary search tree first. Okay, for example, in a binary search tree, like we all know that a set of data can produce different binary search trees if the sequence of insertion of elements are different. Okay, let's take an example. For example, 1 2 3 4 5 6 7 8 and 9. So if we implement it, obviously the binary search tree would be looking like this. Yeah, would be looking like this. But if we like the insertion of element, the sequence, if we put it like this, okay, so the binary search tree would be like in this way. Okay, so now, like, what are the differences in these binary search trees? So if we look into this tree, it looks like a skew tree, isn't it? It is a skew actually, isn't it? But the difference would be here, like let's call it as tree A and let's call it tree B. Okay, now if we calculate, okay, if we calculate the number of the average number of comparisons, okay, to reach a node, if we take the average, then for tree A it would be like 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 whole divided by 9, which is equal to what? 5. Obviously it is 45, right? So the average number of comparisons to reach a node, like for this one comparison, for this two comparison, three comparisons are needed, 4 needed, 5 needed, 6 needed, 7 needed, 8 needed and 9. Okay, so in this way. But in case of this tree, like it is taking one comparisons, then it is taking two comparison, these are 2 and 6, then this level would be taking 3 comparisons and this level would be taking 4 comparisons. Then how many, like average number of comparisons would be like what? It would be like 1 plus, this is 1 and 2, right? So 2 into 2, which is 4, plus 3 into 4 plus 4 into 2, isn't it? Whole divided by 9, which is equal to 1 plus 4 plus 12 plus 8, which is 25. So 25 divided by 9, which is equal to 2.77, isn't it? So here it is 5, here it is 2.77. So we need to understand that, like, here it is 5 and here it is 2.77. So obviously in terms of searching purpose, tree B is more efficient than tree A, isn't it? So see, the number, like the sequence, it depends on the sequence, either this tree would be efficient or not. And we all know that binary search trees, like BSTs, we used to use for only searching purposes, not like insertion or deletion and all. Like it is famous, it's binary search tree after all, so it is famous for the searching purpose, isn't it? Now obviously tree B is like tree A is less efficient than tree B, that's for sure. Now we need to understand that, like this tree, okay, This tree can be considered as a like linked list as well, single linked list, isn't it? The flow of direction like this, there is no way to come back, isn't it? There is no way to come back, only the this direction is possible. Okay, this is not possible. Okay, so looks like a single linked list. Okay, then the searching would take O of n time complexity, isn't it? There is no log n here, but in case of this it's log n. Why it is O of log n? Because it is balanced. Okay, it's a like two-way, like, isn't it? There's no single direction here, so like it's like it's a little bit more balanced. That's why the time complexity is coming O of, sorry, like searching time complexity is coming like O of log n. So this balanced concept actually, like a balanced concept, like which like a binary search tree which would be balanced. Okay, what do you mean by balanced? We will talk about it later. So this height balance, like here in the left subtree, in the right subtree also there are heights, right? So this height balanced thing is completely, this concept is called balanced binary search tree. Balanced binary search tree. This balanced binary search tree is actually called AVL tree. Why? This concept, why this concept is needed, we will talk about it later. Like obviously, basically we will be like in a basic things we can say, like a binary search tree, like we don't have any like control in the way to insert, right? We can't say the users that you have to insert like this, you can't insert like that, we can't say that. So obviously there is no control, we don't have any control of the sequence of insertion, isn't it? So we have to convert this inefficient tree into this kind of tree, and this is where like the balancing comes. Okay, you have to make this unbalanced tree as a balanced tree. Now how, when it would be called as balanced, when it is imbalanced, we will talk about it after a few minutes. Before that, we need to understand that this concept, this balanced binary search tree concept, has been invented by two Russian mathematician. Russian mathematician who are, the first name is GM Adelson Velsky. Okay, another name is EM Landis. So if you like observe carefully, this is A, this is V, and this is L. So this is the place where AVL tree came. Actually they invented it. Okay, they invented this concept, that's why it is AVL tree. Okay, now like to give the honor to them, this balanced binary search tree concept is called as AVL tree. You can call it as a balanced binary search tree as well, but you from now we will call it as AVL tree. Okay, now when the a tree is called an AVL tree, that's a valid question, right? But before that, let me talk about the main aim of AVL tree is to perform efficient searching, insertion and deletion operations. Searching is efficient when the height of left subtree and right subtree of the nodes are almost same. Like for example, this is a node, this is a left subtree, and this is a right subtree. Okay, this is the root, LST and RST. Like here in this tree, this is the right subtree of one, right? This is the right subtree, there is no left subtree, so this is called the imbalancement. The height of the right subtree is 8 and the left subtree is 0, isn't it? this right subtree is having the height 8 and left subtree is 0. This is called imbalancement, whereas here the left subtree height is 2 and the right subtree is 3. So almost same, we can say, right? So the efficient searching is possible when the heights of the left and right subtrees of the nodes are almost same. For every node it has to be, okay, the height of LST would be almost equal to height of RST. Clear? Okay, so this is the concept. Like, now how much closer? Okay, for by the way, this kind of concept, like this balanced binary search tree, is fully possible for full binary tree. I have talked about it already. Okay, full binary tree, also possible for complete binary tree. It's already there. Okay, because full binary tree and concept binary, by definition there has to be obviously balanced height, they has to have. Okay, but this is an ideal situation, but it's not achievable in every time. In real life domain you can't achieve the complete binary tree and full binary tree every single time, right? So if we have this kind of tree, okay, this kind of unbalanced tree, we have to make it like that, and we will be doing it like rotations. We will talk about it later, using rotations, left rotation, right rotation, we will be doing it. Okay, but now here in this case, like an AVL tree is a binary search tree where the difference of the height of the left subtree and height of the right subtree of any node can be all at most 1. This is the definition. Okay, in an AVL tree, the height of the left subtree, okay, and the difference between height of the left subtree and height of the right subtree could be at most 1. At most 1, the difference could be like that. Okay, now it could be -1 or it could be +1. Okay, so, and by the way, this difference, okay, is called actually balance factor. We will be talking about it actually now. Balance factor, you need to know what balance factor is. Now let me draw a tree and we will talk about all these things. Okay, so 20, so the balance factor is equal to actually height of left subtree minus the height of right subtree. Okay, this is the balance factor, and we will be calculating it for every node. Now let's start from the leaf nodes. Okay, so this node, this node, this node, and this node, these are leaf nodes. Okay, so obviously the balance factor would be what? 0, 0, 0 and 0. Why? Because they don't have any left and right subtrees, right? So the difference would be 0, isn't it? But when it's come to this subtree, what would be the balance factor? Obviously it is going to be 1. Why? Because left subtree and there is a right subtree. Left subtree is having the height 1 and right subtree is having the height 0. So 1 minus 0 equal to 1. Yeah. So now let's talk about this one. Okay, so here the left subtree is having 1 height and it is having 2 height, then obviously 1 minus 2 equal to -1. So obviously -1. And in case of this one, what will happen? Obviously it is going to be 0, because like 1 and 1, so obviously 0, isn't it? Now let's talk about this one. So for this node, the balance factor would be obviously -1. Why? Because the left subtree is 2 and right subtree height is 3. So 2 minus 3 equal to -1. So here in this case you can see that like every node is having the balance factor at most 1, isn't it? From -1 to +1. Actually balance factor could be from close interval -1 to 1. This is the range of the balance factor for an AVL tree. So this is an ideal AVL tree. Why? Obviously because it is maintaining the balance factors in the desired range. Okay, but there is an example of it when the tree would be balanced, look like it is balanced, but it is not balanced and it is not an AVL tree. Let me give an example. For example, this is 10. So now balance factor would be 0, 0, 1, minus 1, 2, minus 2 and 0. Now why it is 2 and minus 2? Because you can see the left subtree is 2 and it is 0, so 2 minus 0 equal to 2, and here it is 0 and it is 2, so 0 minus 2 equal to minus 2. That's why this minus 2 has come. Okay, now the thing is, you need to understand one thing, that as it cross the limit of the like this minus 1 to 1, okay, as it has crossed the limit, so obviously it is not going to an AVL tree. Okay, so this is the basic funda of an AVL tree. Now let me talk about the left threaded node and right threaded node, left heavy node and right heavy node. Okay, right heavy node and left heavy node. Okay, so a node is called a right heavy or right high. Another name is right high, and obviously here it is left high. Okay, so a node is called a right heavy or right high if the height of its right subtree is one more than the height of the left subtree. For example, this node, this 56, this is a right high or right heavy node because the right subtree height is one more than the left subtree height. Okay, here also this one, the left subtree is 2, it is 3, that's why it is. So you can see that, okay, if the balance factor is less than 0, okay, if the balance factor of a node is 0, then obviously this is right heavy node. Okay, and if the balance factor is greater than 0, then you can say it is a left heavy node or left high node, isn't it? For example, this, and in case of it is it's like minus 1 minus 1. Okay, so these are the thing, these are the basics of AVL tree which I have discussed, and in the next video we will talk about more on AVL trees. It's a very interesting topic and you need to know how to balance and all everything. These are a little bit of like complex, but when you will be understanding everything, this is going to be very easy for you. So don't worry about that, and like watch out the playlist, stay with the playlist, and subscribe the channel if you haven't subscribed yet, and like please do share the videos, okay, and to your friends so that they also could learn. And obviously let me know in the comment section if any kind of doubt or anything you wanted to like ask or anything. Okay, and this much for today guys, see you in the next video.